Welcome to the fan development environment. This tool was built as a product of my master's thesis. I'm Robert Keegan and this video shall serve the purpose of visualizing the workflow with my tool. At first, open the Python script's main, input and export parameters in your preferred Python IDE. Then open and change the placeholders in the input script so that it meets the customer's requirements. Make sure to comment the unused lines of the form of limitation that are not needed. In the shown Spider IDE, this shortcut control +1 can be used for that and save the file afterwards. Now check the export parameters script of the analytical tool and change it if necessary to satisfy your customer's need. If you change something, make sure to save this file respectively. Then switch to the main script and let it run. The tool will ask you if you want to save all necessary files for the following CFD simulation. However, it is recommended to run the script twice and save it just a second time after having checked all parameters first. Check all plots and the variable explorer. After the analytical predesign follows the transition phase. Here all generated files of the fan need to be copied from the export directory of the Python folder to the projects directory of the fan development environment. Copy the whole generated fan directory to the computer which is going to perform the CFD simulation. In this case, the predesigning and the computing processes are done on the same machine. Then copy the CFD combi script from the projects directory to the folder of the new fan. Open the script in an editor and change the variable project in line 4 so that it matches the name of the fan. Save and close the script afterwards. Open the console and run the bash script of the fan development environment. For the showcase of this video, the Numika software fleet in version 17.1 is used, so the bash script with the suffix 171 is called. Insert the project's name in the console. Capitalization matters in this case. By confirming the project's name with the Enter key on your keyboard, Numika Autoblade is automatically launched and the 3D model of the fan is generated. The fan is valid if the second to last info line reads success. Afterwards, you are asked if you want to proceed with the mesh generation in Numika AutoGrid. By typing Y in the console and confirming with the Enter, AutoGrid is automatically launched. The user has to load the corresponding Python script by hand. This can either be done by pressing the K key on the keyboard or is shown here with the drop-down menus. For now, the script has to be called twice, due to a software issue. By calling the script the second time, the mesh will be generated automatically. This may take a bit, depending on the computational power of your machine. After that, check the mesh quality, and if everything is good, close the program. If AutoGrid generates negative volumes, like in this case, go and see the Troubleshooting Measures section of the master's thesis. In this case, the set constant lines need to be reset to a linear shape at the location of ±3% on the relative fan axis. Also, a finer mesh can represent curved shapes better. That's why the cell width at the wall is also stepped down a bit. Then generate a new blade to blade and a new 3D mesh afterwards. After the mesh generation, check the mesh quality again, and if everything is fine, save the mesh and close the program. Otherwise, repeat this troubleshooting step. The bash script asks you now to proceed with the simulation. By typing Y, Numica Fine Turbo is automatically opened and the Python script for the simulation of the fan is executed. The simulation settings are automatically set by the script. Check them and save the run file. Open the Task Manager and create a new task. Also create a new subtask and load the corresponding run file for this fan. Set the subtask to either sequential, parallel, or like in this case, parallel partitioned computation. Then open the settings menu and add as many processing cores as you like and your system can afford. Apply partitioning and give the static requested memory a bit more headroom than initially estimated. Close the settings and make sure the correct solving algorithm is selected. Save and start the task. For better visualization during the computation, switch back to Fine Turbo. Wait until the computation iterations have started in the Task Manager and then open the graphic control monitor. For live data, set the monitor to auto-update. Now you need to wait until the convergence criteria is satisfied or all values have reached a steady state. Then stop the task. Make your first analysis of the fan configuration in the graphical monitor and close it afterwards. By starting CFU from the Find Turbo project, the correct run file is automatically selected. The user has to load the corresponding Python script now by hand. This can either be done by pressing the K key on the keyboard or is shown here with the drop-down menus. By executing the script, a results folder is generated in the fan directory and screenshots of the most common needed results are saved. After you carried out your necessary analysis of the simulation, close CFU and Find Turbo. Congratulations, you now got a fully pre-designed custom fan ready for further optimization. Thank you for your attention.